So hello everyone, welcome to the third Quantum Club. First of all, I want to announce the next Quantum Club that will be in exactly 1 week here with Luke Raidmaker, and the warm-up will be done by Ivo, he's a PhD student, and it will be about 2D materials. Today, after the talk, there will be an apéro as usual, so don't leave too fast. And finally, so what we are going to do today is talk about quantum non-locality. Our dear guest is Nicolas Brunner, who is professor at the Group of Applied Physics here at University of Geneva. And his main research interests are the study of non-locality through different tools, such as joint measurability and entropy inequalities, and also in different contexts, such as quantum networks, for example, and device-independent quantum cryptography, and much more. And before his talk, I will do a little presentation about the EPR thought experiment. So, of course, I will talk about the paper, its motivation, the thought experiment, and the conclusions that the authors got from it. And then about the reaction of other physicists and Bell's theorem. So it all begins with the Heisenberg uncertainty principle. In quantum mechanics, the state of a system is described by a wave function, and observables that we can measure about the system are described by operators that act on the wave function. And if we measure an observable, we will get as a result one of the eigenvalues of the operator on the wave function, and the wave function will collapse to one of the eigenfunctions. So the Heisenberg uncertainty principle says that if two operators don't commute, then the corresponding observables cannot be measured simultaneously. And for position and momentum, we get that the commutator is not equal to 0. And so we get the famous inequality where the uncertainty on x times the uncertainty on p is limited from below. So if we get some measurement of x, then we are limited on the preciseness of the measurement on the momentum that we can get. So what does it mean? This is the question that those three people asked, Albert Einstein, Boris Podolsky, and Nathan Rosen, and they wrote about it an article in 1935, where they got to the conclusion that quantum mechanics cannot be complete. So for them, this relation can imply two things. Either the position and momentum actually don't have a reality simultaneously, or quantum mechanics is an incomplete theory. And those two affirmations cannot be wrong at the same time, because if x and p do have a reality simultaneously, it would be described in our complete theory, but in our complete theory there is the uncertainty principle, so it's impossible. To analyze those hypotheses, the authors formulated two criterions. One criterion for the reality of some quantity and the other one for the completeness of a theory. So according to them, physical quantity is physically real as soon as we can predict its value without disturbing the system. So if we know about some particle, its position exactly without disturbing it, then its position is physically real. Now, a theory is complete if for each element of physical reality we get an element of the theory. And so the thought experiment that they imagined is the following. Let's say we have two particles that are both described by a wave function. So we have psi1 and psi2. The particles interact, and after the interaction, we don't know anymore psi1 and psi2, we only know the common wave function, psi. And that depends on the particle 1 and particle 2, of course. Now, imagine we have the momentum operator on the first particle, and it has eigenfunctions that we call up. So up form a basis, and we can write psi in this basis. We'll have some coefficients, and the coefficient that we call AP depends on the second particle. And actually now we can choose psi that way that AP will be functions of the momentum operator on the second particle. So now, if we measure the momentum of the first particle, we'll get some eigenfunction up, and the whole wave function will collapse to one of the elements of the sum. And so we'll know for sure in which state is the second particle, and we'll know for sure its momentum. We can do exactly the same with position. We have the operator, its eigenfunctions. We write the whole wave function in this basis, and we choose bx to be eigenfunctions of the position operator on the second particle. Now we do a measurement on the first particle. We can measure either the momentum or the position. Let's say we measure the momentum, we get some eigenvalue, and now we know the state of the first particle, and we can deduce from that the state of the second particle. And we do exactly the same with position, so if we measure the position of the first particle, we know exactly the position of the second particle. So what's the problem here? Well, without disturbing the second particle, we could predict with certainty its position and its momentum. And the thing is that it happens at the moment of the measurement. So we decide what we measure. At the next instant, we can know its momentum or its position for sure. So according to the criterion of reality, those two values, those two physical quantities, must be real. And if our theory is complete, then we must have a corresponding element of the theory that corresponds to those two quantities. But this is forbidden by the uncertainty principle. So they deduced from that that quantum mechanics is an incomplete theory. So scientists reacted to that very quickly, and Borh wrote an article just a few months later, also in 1935, where he argued with this point. And his idea was that in the reality criterion, there is a detail that was not taken into account, and it is that the measurement of position and the measurement of momentum are fundamentally two different things, and we cannot combine them, and we cannot say that x and p are real simultaneously. The example that on which he bases his point is the double slit experiment. So we have a source of particles, then we have a double slit, so a wall with two little holes, and then a screen. And particles, they go through one of the two holes, and then they appear on the screen. If our double slit is fixed, we'll get the interference pattern. So the interference pattern says to us that we don't know anything about the position of the particle, and that's because we assume that the double slit is fixed. So when the particle goes in one of the holes, it bumps against the wall, and by conservation of momentum, it has to have the exact same momentum after it went through the hole that's before. So we know its momentum when it goes on the screen, right? And that's why we don't know anything about its position. Now, if our double slit is not very well fixed, it can move a little bit. And when the particle will arrive on the double slit, let's say it goes to the upper hole, then the double slit will move a little bit up. And we can measure this movement, and we'll know for sure that the particle went through the upper hole. And the same thing with the bottom hole. So we will break the interference pattern, and we will get just two lines. But in this case, we don't know anything anymore about the momentum of the particle because we don't know what exchange went on here. When the particle went through, it gave some of its momentum to the double slit, but we don't know how much. So that was Borh's point. And Borh and Einstein had very long discussions about this topic. It lasted for several years, but the debate was settled by John Bell. And actually it was done a few years after the death of Einstein and the death of Borh. So he argued that, okay, if we have a theory that is incomplete, it means that we have some hidden variables. And in 1964, he proved that quantum mechanics doesn't allow local hidden variables. So it's a theorem called Bell's theorem, and it is written on this blackboard, so very short. He came up with a very special quantity here that in classical mechanics is limited to 2. But in quantum mechanics, and we can prove that experimentally, this quantity can go up to 2 times square root of 2, which is of course more than 2. And this proves that some quantum mechanical phenomena, such as entanglement, cannot be explained classically. So classical mechanics are not sufficient for that, and that's why there are no hidden variables in quantum mechanics. And I would like to finish with a comment that Bell did about his proof. So he said that the only thing that he proved was actually lack of imagination. Thank you very much. So now, if you don't have any questions, maybe you have questions.
Many people in the audience. So thank you very much to the Quantum Club for the kind invitation. And also let me congratulate you for your new idea and all the enthusiasm and effectiveness that you had so far in creating it. I'm very impressed. And I hope it will continue for many more months and years and so on, become a tradition. Okay, let me also thank Alexandra for the very nice introduction to the EPR paper. That is really the beginning of this long story of quantum non-locality that I will try to summarize today and hopefully entertain you with these ideas that I find quite fascinating. So let me first start by a sort of Oh, no, j'ai juste pas fait that. Okay, so I'll start with a sort of timeline that is also a sort of guide through what I'm going to say throughout the talk. So, as Alexandra said, the beginning is this famous EPR paper that discovered essentially this phenomenon of entanglement and argued that quantum mechanics is at best incomplete in its known form. Right? Then the key breakthrough came 30 years later by John Bell, right, who initially also liked very much that idea of Einstein, right, that there should exist some hidden variables. So he was motivated to find them, right, to make a full theory, a complete theory of quantum mechanics. But very quickly he realized he couldn't do it. And then he had that great insight that the reason why he could not do it is that because it's impossible, and he proved that it's impossible, right? So that is the content of this famous theorem by Bell. Of course, a key part of this theorem of Bell is that this long debate between Borh and Einstein also becomes concrete now. This is something that you can go to the lab and make an experiment, and the experiment will tell you if Einstein was right or if he wasn't, right? And so that was later developed by some people that I've shown here, notably John Clauser. First experiments came in the 70s and early 80s, and they demonstrated the effect of quantum non-locality. Of course, the most famous experiment is this one here by Alain Aspect. And after that, you know, the mentality changed completely, because now that this strange phenomenon of entanglement became a sort of experimental reality, people thought, okay, what can I do with it, right? So then in the early 90s, Arthur Eckert had that brilliant idea that with entanglement and non-locality, you can do quantum cryptography. Okay, so something that is really a breakthrough in computer science. And then I will also talk about some nice experiments and some more recent ideas and research lines. Okay. Well, as said, these topics got a lot of publicity and recognition, in particular these 3 people that got the Nobel Prize last year for playing a key role in all this story. All right, but let's go back to physics, and what I want to start with is to to try to go back to this question of EPR in sort of very basic terms, okay? So imagine that you have some experiment, right? And what you want to know is, can I explain that experiment within classical physics, right? That's the question. So let me take it to the simplest possible thing here. So imagine I have some device here that is represented here, and this would be a black box device, right? Okay, I know it's a blue box, but the spirit is black box, right? So the point is, I have no idea what's inside. I can play with the device, right? I can choose an input that I call X. I get an output, right? So inside the device, there is some physical process going on that will generate A as a function of X. But again, this is totally oblivious to me, right? Now, what I want to do, right, is I want to do this black box test of physics. So I want to know if from the data I get from this device here, right? So I play with my device many, many times. Each time I choose an X at random, I get an A. So I collect this data, right? P of A given X. And so from this data, I want to know, is the underlying physics in this box classical or is it quantum? Right? That's the question. And of course, I would be very happy if I could reject classical physics as an explanation of what's going on, right? This is what I want to do. But obviously, if you think about it, this is very challenging, right? How can I possibly prove that some black box, just based on data, is incompatible with classical physics? So classical physics is a huge thing, right? You have mechanics, you have electrodynamics. There are many, many possibilities, you know, for implementing this box here within classical physics, okay? So, well, you are the quantum club, so I'll give you a sort of insight on or hint on how you could do this, right? So you most probably heard about quantum computers already, right? So quantum mechanics allows for very astonishing devices that can take as input a very large integer n, and then they will give you as an output here two numbers, p and q, that are prime, and you can check that they are the factors, the prime factors of n. Right? And so suppose you do this experiment and you check that, you know, you take n that are larger and larger, but the device, even maybe with a constant time, will spit out to you these numbers. So you're impressed, right? You know that classically this is a very hard problem, right? So intuitively you think, aha, it cannot be classical what's inside there, right? But now you see the real question is, this is not only the intuition, I want a proof, right? I would like to from my data to prove that it cannot be classical physics. Okay? So here you see I'm at a dead end. That thing cannot work, right? Because the first reason is that we don't even know in computer science whether factoring is a hard problem or not, ultimately, right? It's just that the best algorithm known today is not efficient, right? But there might exist an efficient one. And you see, even if it would, I mean, classical physics doesn't prevent me from putting an ultra-powerful classical computer inside the device, right? So there is nothing in classical physics that would, you know, limit my ability to simulate quantum mechanics within this device, okay? So like this, it's a dead end. Like this, it can never work, okay? And you may think maybe it just never works in general, right? But that is actually wrong. It can work, and that was the key insight of Bell. And so to make it work, you have to go, instead of having one device, you should have two devices now. And these should be separated, okay? So that was the key idea of Bell. This is the same photo that Alexandra showed, and indeed here you see the underlying set. Okay, but let's go step by step. Let's go back to my blue black boxes, right? And now I have two of them, right, at a distance. That one is held by Alice, the other one by Bob, and you see it's the same thing. Each one has inputs and outputs, okay, and so I can play with that experiment, repeat it many times, and then I get data, right? So what is my data? My data is the probability to see some outputs, A and B, given the inputs that I chose, right? Okay, so now if I do that experiment, for example, with quantum particles, as we will see in a minute, well, the first thing that I observe is that my data doesn't factorize, right? So it's not independent behavior here and there. There is some form of correlations, okay? And so I want to know how it works, and in particular, I would be very happy if I find a mechanism within classical physics, right? In classical physics, how can I generate correlations between two distant events? Well, I can do it via signal, right? So maybe when this box gets some X, well, there is some emitter hidden there, it sends a signal to the other side, and of course, this explains why there are correlations. To rule it out, of course, it's very easy, right? I put my devices far apart and I synchronize my experiments. So if I get a space-like separation, at least within standard classical physics, I'm happy to say that there can be no signal, and so therefore this is not what is going on, right? But of course, in classical physics, there is a different way to, to mediate correlations, right? And that would be via a common source, right? So suppose my devices, they came from the same provider, right? So then, well, then it's natural, right, that they behave in a correlated way because they are fabricated in the same way. It's the same sort of program inside, right? And so this program, well, I want to represent by some classical variable that I call lambda, okay? And in fact, these lambdas, this is exactly what Einstein had in mind when he talked about local hidden variables. Okay? It's just that here there is no point to make them hidden, right? And just say that these are lambdas and then they go inside. I don't want to say anything about the complexity of this lambda. It can be, extremely complex. I just want to say that this is some sort of classical program, so I can represent it by a classical variable. Okay, and of course now, well, I want to ask, can I test this hypothesis here, right, as a mechanism for the correlations I see? Okay, so at this point, if you think about the question, well, there are some correlations due to a program. So suddenly I can imagine some sorts of program, and then I can see if with those programs I get the data that I had in my experiment, right? And if it's not the same, okay, then I can rule out that program. But how can I rule out all programs, right? This is much more challenging because there are infinitely many of these programs, right? And they can be of arbitrary complexity. Okay. And so that was the brilliant idea of Bell to show that, in fact, even with a very simple setup, you can actually challenge this hypothesis of a common program. And so this is what led to the famous inequality of Bell. Okay, but I like to present it in a sort of simpler and more fun way, just as a sort of game. Okay, and so this game, well, it's a very simple one. It's a game where Alice can ask in each round one out of two possible questions, right? Let me just write them: x equals 0, x equals 1. The answer will be binary, right? And at Bob's side, it's the same. Just two possible questions and binary answer. Okay, so you see it's a very simple experiment. Now, there are some rules in this game, right? The point will be that, remember, this is a game I play many, many times, right? And in each round, Alice will choose at random x equals 0 or x equals 1, right? And Bob as well, at random y equals 0 or y equals 1. And so ultimately, if I repeat millions of times, of course, all four possibilities will occur, right? And so now what I set as the rules of my game is that depending on which questions were asked, right, that I want to see different relations between the answers, okay? So you see, when Alice asked question x equals 0 and Bob asked y equals 0, I want to see the same answers, okay? This is this green line here. Okay, so I mean that I'm happy if the answer is +1 here and +1 there, or if it's -1 here and -1 there. It's the relation that is important, right? Now, okay, you understand the rest of this diagram. If I have question x equals 0 and y equal 1, I also want to see correlated behavior, right? The same answers, x equal 1, y 0, it's the same. And then there is this last part of the game, this is what makes it interesting, that whenever you have x equal 1 and y equal 1, you want to see opposite answers, right? So plus 1 minus or minus plus, right? Okay, so you see it's super simple, right? Now, you may see it already, but in fact, this game has a sort of constraint in it, right? There is some sort of frustration in this game. Now, remember what is the point of Bell? The point of Bell is that when you play this game, right, by putting any sort of program here, you will get some limitation, okay? So now it's a nice exercise to imagine that you are the person, right, who programs these devices. You come up with the lambda, and the point is that you should get the maximal score at this game, right? So remember, it's played many, many times. In each round, it will be one of these 4 possibilities, and you get a point whenever you get it right. Okay, and if you don't get it right, then you lose a point. Okay. So how will you go on by programming these devices? Okay, so the first thing is you have to tell Alice's device what to do for the first question. Okay, we need to start somewhere. So if it's the first question, okay, let's just say the answer is plus 1. Could also be minus, but okay. Here we start with plus. Now, okay, so what should we do for Bob's device when the question is y equals 0? Obviously, now we have no choice, right? It should also be plus, because then we will satisfy this relation, okay? But now, you see, remember the key part of the game is that in each round, Alice chooses at random, and Bob chooses as random as well, and they are separated, they are far apart, right? So the point is, from the point of view of this device, there is no way to know what question was asked on the other side. Okay, so if I get the question x equal 1 here, it might very well be that Bob asked y equals 0. Okay, so for x equal 1, I have no choice. I also need to program plus, right? Then I get this one right. And then you see how it continues. If I want to get this one right, I also need a plus. Okay. And now I finished, but I see I have a problem, right? Because the last one is not correct, right? I have plus, and I wanted different. So ultimately, I did quite well, right? I did 3 out of 4, but I didn't do 4 out of 4, okay? And you will say, oh, it's totally trivial, right? That you cannot do 4 out of 4. You're right, it's totally trivial, but that is essentially Bell's inequality, right? So first of all, it's correct. You can formally prove it that this score is upper bounded by 3 out of 4. And that is true for any classical program. And that is simply Bell's inequality, right? It's nothing more. Okay? So far, so good. You can ask questions whenever you want. And it's better that you stay on the train than getting lost until the end. All right, so all this thing we can also do more formally. So I knew that finally the Mac PC confusion would show up somewhere. Okay, so here it is. All right, maybe I just write that equation on the board. So the point is that in all of this is hidden this idea of Bell that is a form of locality, right? So the idea of Bell is that my data, let me write it down here, my P of, so my data P of A, B given X, Y, okay? So you see, if my experiment can be explained, right, by these hidden variables, the point is that, of course, I'm only allowed to see the data, right, which is this part. And the data will be the average over these hidden variables, right, to which I have no access. Okay, but if there exists such an explanation, then this data, you can write it like this. It's an integral over lambda. There should be some distribution of these variables, right, these lambda, some q lambda. I don't know what it is. It's just a valid distribution. And then the point is that there should be some sort of response function, right? So on Alice's side, there should be a probability function to get the output A, and that depends on x and lambda, okay? The input x and the lambda here. But very importantly, this thing doesn't depend on y, right? Because y is separated, and so that's exactly the idea of locality. And then on Bob, it's the same, right? There should be some other response function that will generate B given y and lambda. Okay? And so that is what we call the locality condition of Bell. Okay? So whenever you get data, and whenever this data can be decomposed in this way, you say, okay, this I can understand with a classical program. This is local. And whenever you cannot, then it's non-local, right? And so the possibility on how to test this assumption, right, this locality assumption, is to go to Bell inequalities. The most famous one is this Clauser-Horn-Shimon-Holt expression, which is written here. So this is, you see, just a linear function of these correlation functions, right? This would be just, you see, the probability that the outputs are the same minus the probability they're different. And if I sum these four things, this is upper bounded by 2. But again, that expression is just exactly the same as this, right? It's just saying the same thing, that the score in this game is upper bounded by 3 out of 4, right? Okay, good. All right, so at this point, what did we do? Okay, so we introduced this idea of an experiment with 2 distant boxes. And so then we said, perhaps even quite trivially, that if there is this common program, okay, well then we have a limit on the correlations that we can see. Okay, and really here, there is nothing complicated. It's almost trivial, I would say, right? What is not trivial is to come up with that precise game. Okay, that's the great point. But to prove that there is a limit, this is just a total triviality. Okay, now let's make it more exciting, and we are going to try to play this game with quantum mechanics. Okay, so instead of having a classical program, I have a quantum program. Okay, and so what is a quantum program? Well, it could be, for example, some entangled state. Okay, so now my source here would, for example, produce a pair of photons that are entangled in polarization, right? So polarization is like a spin half. And so I could imagine having this sort of singlet state for my 2 polarizations, okay? Now, each photon goes into the lab, but again, now you see here I will provide an input, right, that may change the measurement of the polarization. I'll need to provide an output. So if I want to complete my strategy, I have to say what I measure, right? So this I can do by just specifying some Borh vectors, right? Or some directions in which I measure the polarization. So then you do a bit of algebra, right? You compute what is the score for this quantum strategy. And so, well, it's very easy. Again, let me just skip the calculation here. But when you do that, you find that this expression S here, this is now 2 times root 2, okay, which is obviously larger than 2, right? So remember, this S is this thing here, right? And we did this proof, right? It's essentially trivial, but now it's really astonishing, right? In quantum mechanics, I can go beyond. And so this is what we call a violation of Bell's inequality, right? And you see that now this is no longer a philosophical debate, right? This is something I can test in an experiment. I can do that experiment, I calculate this S, and then I check what it says, right? I'll come back to experiments in a minute, but let's just conclude now with this theorem of Bell, right? That works in 2 parts. First, you show that in certain type of experiments, correlations in classical physics, right, must be limited, right? Of course, this idea of locality applies to classical physics in general, right? But basically, this is the point, right? That ultimately there exist quantum experiments that show correlations that are stronger than what you can ever expect in a theory that satisfies this idea of locality, right? And so that is what we call quantum non-locality, and this can be tested in an experiment. Okay, that's the point. All right. So let me maybe move now directly to these experiments. Okay. So as said, the first ones were done in the 1970s. Before there was simply not, enough technology there, but there was a lot of progress made in optics. And so what people managed finally to do is to create these entangled states here, okay? Very bizarre, okay, never mind. So the point is, how do you create these entangled states? You can use an atomic cascade, right? So this is some ions of a particular media that you can excite, right, to this level here. And when the atom decays, well, there will be a first photon emitted here. Here there is a sort of metastable state, and that quickly decays there. And so the point is, you can separate these two photons because they don't have the same frequency and they have opposite momentum, actually. And they can be entangled in their polarization, right? Because when you decay here, it might be that this photon is H and then this one must be V by conservation, or the opposite, right? Because you don't know which one it was, it's totally indistinguishable. It's just the superposition of the two, right? So that's how you create entangled states. Okay, so here were the first experiments that you see. Clauser was one of the first to make an experiment. He could observe some Bell inequality violation. Then you may ask, but why is it that this is this Asper experiment 10 years later that somehow got all the fame, right? This one is much less known. Well, it's because Asper's experiment managed to introduce a key element. I see that the next slides, they are totally messed up. So maybe I switch to the PDF. Is it okay? Because here otherwise did you stop the PDF again? Ouais. Super. Il faut on va se mettre en lecture. Droite. À droite. Ah ouais.
Ah,
super.
thank you.
Ok, merci beaucoup.
Okay.
Ok. Much better.
Désolé, peut-être j'enlève quand même la barre.
Trop bien.
C'est ça.
You can set it.
C'est ça?
Super, merci. Okay, sorry for the technical issues. Aha, okay. So let's go back to these experiments. I like these very old drawings from the papers, that were done manually. So here you have the setup of Asper's experiments. Oh, maybe this is, okay, so this is the first experiment by Clauser. It's essentially like this, right? So you have this source, it produces these two photons at different wavelengths that you can separate, and then you put these polarization analyzers here, and then photomultipliers, right? You just detect the photons. And then you monitor everything, and you repeat, and you estimate this CHSH parameter. Okay, so why is that experiment of Aspe in the 1980s that famous, right? Because it introduced really the space-like separation in a very convincing manner, okay? So you see in the previous experiments, that was done here with analyzers, right? With polarizers that were at a fixed position, okay? So first you would test one alignment, repeat 1,000 times, then you change it, you test the second one, and so on for all 4 of them, right? But of course, if you do the experiment like this, well, then you can not exclude an explanation where there would be some sort of signal sent from here to there, right? Then there is no space-like separation in this thing, right? So to bring in really the space-like separation, you need somehow to be able to switch at random between the measurements, okay, here and there, okay, and this is what Aspe was able to build in a very clever way, okay. So essentially, you see in this version of the experiment, you have 2 analyzers now, one for A and one for A prime, okay. This would be our question x equals 0, this is x equals 1, and you have the same thing on the other side. And then there is this funny device here that allows you to very fast switch between the beam going through, and hence to this analyzer, or the beam being deflected and therefore coming to the second analyzer. Okay. And so the way Aspe did this is via some electroacoustic device, okay, that you can set very quickly, and therefore, given the speed of this device, this allows you really to get a separation, a space-like separation between here and there, right? That was a very ingenious idea. Okay, so you see the switch time is 10 nanoseconds, and this is much faster than the 40 nanoseconds that light would need to go from here to there. Okay, so that's why this experiment was really groundbreaking. And so Aspe observed a very nice Bell inequality violation. Here you see 2.4, but perhaps even more importantly, he observed that all sorts of experiments he could do with this setup, they matched extremely nicely with the predictions of quantum mechanics. Okay. Okay, so here's some nice photos of the 80s. Yeah, you see it's impressive to think about the progress that has been achieved. I mean, nowadays, all of this thing would hold on a small table like this, right? It would work 100 times faster, 100,000 times faster, and so on. The only thing that did not change is the mustache of Alan Aspe. Okay, so then there were lots of experiments, of course, that tried to reproduce and confirm these observations, and that was always the case, right? Non-locality was always observed again. Of course, here in Geneva, we need to mention the very nice experiments that were done by Nicolas Brunner, and also by Wolfgang Tittel at that time, who was a PhD student, and he's our colleague now back in Geneva as a professor in our department. So that experiment, it was done in '98. It was very impactful because it was the first one that brought this phenomenon of entanglement and non-locality outside of the lab. Okay, so the experiment of Aspe, it was done with Alice here and Bob there, basically, right? Okay, a bit longer probably, but this sort of distances. You may think, okay, maybe in the lab I can observe this very astonishing phenomenon, but maybe when I go to longer distances, this all vanishes, right? Maybe there is some sort of different physics here that prevents from long distance non-locality. And so in this experiment, what they did, well, it was exactly to test this idea. They created entangled photons. Okay, here Geneva means here actually, or the Ancienne École de Médecine to be precise. And then they managed to send these photons through telecom fibers to 2 villages around Geneva, to Bellevue and Bernay, right, that are separated by more than 10 kilometers. And still they could see very nice Bell inequality violation. So this proved that that these very astonishing effects is not an artifact of the lab, right? You can really go out and see this.
Why didn't do one of the experiments in Geneva?
Sorry?
Why did they have to move both of them outside? Why didn't they move only one of them?
Well, you see the distance here is less, right? and the point is that, well, it's okay. You see the setup, no? That you have the source in the middle and that you send them out in opposite directions. So it's nice to do it with that geometry. But you're right. You could, in principle, keep them inside here. Achieving space-like separation is, of course, much easier like this, right? Because if you keep one photon in a loop here, you see it's much less stringent, the locality condition, right? Again, some photos of the experiment. You see young Wolfgang here. And here you see the setup, right? So the source is more or less here, and you see Bernet, Bellevue, they have this nice east-west alignment. You can also see that the canton changed a lot, right, during all this time. So you see the airport here is surrounded by fields, which today looks completely different. Okay, and then I would say there came all sorts of experiments connected to Bell. I won't go through all of them, that would be way too long. Let me just mention some key ones. So key ones were, for example, these two 2015 loophole-free experiments that, you know, somehow show in an even more convincing and sort of final way this effect of non-locality. We can come back to it later if you want. Let me also mention this interesting experiment done also in Geneva, 2002. That is the so-called before experiment. So this is a very nice idea where you do an experiment with analyzers that are moving. So again, you see you can implement these moving analyzers by some electroacoustic devices here. And so you can say that somehow the choice of measurement is done by the speed of this acoustic wave here. And so because you see they move apart like this, you can create a situation where, you see from the point of view of relativity, each of the observers measures before the other one. Okay, so it's a nice idea because you see, you may still imagine that somehow maybe it's a form of communication that explains these effects. It's just that it goes faster than light. Okay, it's a bit unusual, but why not? Okay, imagine that there are some particles, some tachyons, right, faster than light. But then in this before analysis, you can rule out this sort of idea, right? Then if you want to have a communication, then it should be with respect to a preferred frame, which is then taking you into more and more exotic physics, I would say. All right, so let me move to another idea. How long do I have?
10 minutes.
10 minutes, okay. So then let me move to something else. So you see, once you see all those experiments, right, and you can think, okay, now, well, seems like these strange phenomena are a physical reality. Okay, so if they are there, then what can I do with it? Okay, and that was one of the key ideas that led to quantum information processing. And so this is essentially the realization of this person here, Arthur Eckert, who in the 90s realized that you can actually use entanglement for secure communication. Okay? And so essentially the idea is that if you imagine building a secret key out of the result of these measurements here that you will do in your Bell inequality test, you can somehow argue that they are secure, right? Because somehow, if there would be an adversary, right, that could, for example, prepare these systems and predict A and B, that would be like having local hidden variables, right? And so therefore, if you can prove that there are no local hidden variables via Bell inequality violation, this should prove that the key is secure. Okay? So that was the intuition of Eckert. At that time, he couldn't really prove it. It was a nice intuition that turns out to be correct. And in fact, this is something that you can even strengthen, right? And so that leads to this concept that is known as device-independent cryptography, where the point is that you would like to generate some secret key between Alice and Bob, but using truly black box devices, right? So you could even imagine that it's the adversary that prepared the devices and that gave them to Alice and Bob, right? So for example, these devices could be tagged by NSA devices, right? Whatever. In cryptography, it's a very standard scenario. And so the point is that, you see, even in that sort of dramatic case, right, where it's the adversary that sets the cryptographic devices, there is still a way via Bell inequality violation to ensure and to guarantee, in full generality, the secrecy of the key. Right? And so if you want, the idea is that the key rate, right, so how much key you can extract from it is given by okay, let's say 1 bit per round, right? Minus some correction due to the errors, right? You have to correct errors. This is a correction with entropy here. And then there is a correction due to Eve's potential knowledge, right? And you see the very interesting thing is that Eve's knowledge is bounded by this S value, right? So this is our CHSH expression. Okay, so non-locality will limit the knowledge of Eve about the key. So this is something that, okay, colleagues and I developed a long time ago now. Initially was only of interest to theorists, of course, but in recent years, people in the experimental world also got interested in this, and there was a first proof of principle experiments done only a couple of years ago in different groups. All right, so let me go through a few other recent developments. This is indeed also something I'm interested in. It's non-locality in networks, right? So instead of having just our Alice and Bob setup with one source, imagine something like this, right? Where you have many sources and many other parties that are the nodes of this network here. And of course, in such a setting, you can also ask questions about non-locality. And in fact, what is interesting is you can even generate and demonstrate stronger forms of non-locality. Okay? The reason for this is that here, of course, you can play with the entanglement of the states produced by all these sources, but there is another form of entanglement that you can play with, namely the measurement that is done in this box here. Right? So you see, before you had only one leg coming into each box, while now you can have more, right? And when you have more, you can ask about performing some joint measurements on these two systems that have eigenstates that are entangled, okay? So this is what we call entangled measurements, and this is what you use, for example, when you do quantum teleportation or processes like this, right? So this is another way to generate correlations that can be even stronger than what we have in the standard Alice and Bob configuration. Okay. Some other interesting development a couple of years ago, it was proven through the use of these ideas of non-locality that you can have a real advantage for a quantum computer in so-called non-oracle cases. Okay. So you may think, okay, but this was known since a long time that there is an advantage for quantum computing, but okay, that's actually not rigorously true, right? If you think of factoring, for example, it was known since a long time that you can factor efficiently quantum mechanically, but it's not proven that classically you cannot do it, right? But here there is actually a proof in this paper. This is not for factoring, for different types of problem, but it's interesting because the key idea in it, or the key tool is non-locality. All right, maybe one final other direction that I like is the study of non-locality beyond quantum theory. Okay, so what does it mean? Well, so nowadays, you see, we have a sort of geometrical interpretation of correlations and of non-locality. And so in this geometry, you have a, sort of the simpler set, the blue one here. These are the correlations that you can get in classical physics, okay? So these are the ones that are bounded by Bell inequalities. So then, if we go to quantum theory, then we have a bigger set, right? Because we know that we have stronger correlations in quantum mechanics. So this is the green one. But then you can ask, okay, can I even go beyond, right? So can I have correlations that I cannot do in quantum mechanics that have this idea of non-locality, but that do not allow for signaling at a distance, right? That's an important part of it. And this is actually possible, right? You can, if I go back to my CHSH game here, I can even get the maximal score of 4, right? So this would mean that in my little diagram, I win all the time, right? With probability 1. And this is possible within a model that, satisfies causality, right? And so this has motivated then people to investigate what is special about quantum theory from this perspective, right? You see, initially some people argued that maybe, the fact that quantum mechanics allows for non-locality, right, could be a sort of unique feature of the theory, right? And so maybe that instead of these very complicated and bizarre axioms of quantum mechanics, like you need Hilbert spaces and stuff like this, maybe you could phrase quantum mechanics based, for example, on the hypothesis of non-signaling, okay? That would be much nicer if you, as an axiom, you said events that are space-like separated cannot influence each other, right? But that turns out to be wrong. It's not an identifying feature of quantum mechanics, because you can get theories that are even more non-local than quantum mechanics, yet they are non-signaling, okay? But then people thought, okay, even if it's like this, maybe then these super quantum models, right? Maybe they have some very undesired or strange physical properties, right? And so if we understand what we can do with these more general models, maybe we then get an intuition of what somehow limits quantum mechanics. And so this has led to very interesting ideas. For example, also connected to computer science, people have shown that if you would have access to some of these edges here of this yellow set, you may have a power of communication that becomes essentially infinite, right? That you can solve extremely complicated problems or distributed problems with just one bit of communication. Okay? And this is something that is believed to be extremely unlikely to happen, right? So these are interesting ideas that also give a new perspective on quantum mechanics and its foundations. Okay. So maybe let me conclude here. Well, I had to mention this famous quote of Bell. Of course, all this is, you see, it's beautiful. It led to things that are even becoming concrete and practical, like quantum information processing. But ultimately, I believe the beauty of it is just fundamental physics, right? Try to understand what's going on in the world. Okay, merci beaucoup.
Are there any questions? You can ask them now, or if there are no questions now, we can continue the informal atmosphere in the afterward. But if you have some, then please continue. Oh, otherwise, I have one. So when we were talking about networks,
okay.
I heard some protocols that you don't need actually the random input there, and I guess it can close one of the loopholes, because now we have kind of quantum random generators or random generators, but they also have predictability, and I guess in some papers of Antonio Assi and others that they prove that actually if has some connection to source or to measurement devices, then she can still predict something, even if we have perfectly random source. That are there any experiments with networks where they actually didn't use random input?
Okay, that's a great question. I see that you know a lot already about all of this. Okay, let me show you. I had an extra slide on this thing. Yeah, okay, maybe let me explain it with this. It's all cryptic, but I just need the diagram of this little triangle. So you're fully right that one very astonishing thing in these networks is the fact that now we can actually have a setup like this one, right? Okay, this is what we call the triangle network for obvious reasons, where somehow now you have three independent sources, right, that distribute entanglement. And so inside these devices, you can do this famous entangled measurements, right? That I wrote down here, it's not too important. But what is astonishing, right, is that now the statistics that you get is non-local, okay? You can prove that you cannot reproduce the same behavior if you would replace these sources by classical variables, right? But the astonishing thing, as you mentioned, is that now there are no questions asked, right? It's always the same question, okay? Because you see there is a line going out, but there is no line going in here, right? Of course, if I go back to Alice and Bob and to all I said, remember this little game with the diagram, it's crucial that you have questions that are chosen at random and that cannot be predicted in advance, right? Otherwise, it's all trivial. Okay, if you can predict the questions in advance, you can generate bits that are correlated or anti-correlated. It's only hard if you cannot know in advance, right? But in this setup, you can actually get rid of these measurement settings, okay? And you're right that indeed also in Bell experiments, people have argued that this choice of measurement settings should be really random, and so how do you ensure it? And this is, okay, it leads to all sorts of questions. And here it's nice because somehow you can bypass these questions because you need no inputs, okay? But, there is a but, you need an assumption that is, in a sense, related to the fact of having independent inputs, which is that you need these sources to be independent from each other, okay? So somehow you see you trade the use of inputs for independence of sources. Okay? And in a sense, it's a bit related. It's not exactly the same, and it could lead to very interesting protocols where, for example, you could certify the randomness of this measurement outcome here, as I mentioned, although you need no input randomness. But, okay, you need to assume that the sources are independent.
But if we use, for example, ideal triangle, then the length between the source, they're the same as the length between the stars, they're the same as the length between the star and the party.
Yeah.
Then in this sense, I guess, if we can make it just a bit not triangular, but a bit far away, that we can assume that light propagates faster from the middle of the triangle to the next party, then they're kind of independent.
No, Aha, so you say that if we would actually time all of this here.
Yeah, so a bit outside the triangle, then I guess it should go.
Well, yeah, okay. So of course, in a sense, you could say my physical sources are separated. That's true. But you see, then you could, you know, if you think of a fundamental test of nature, you could also think that nature somehow distributes correlations, for example, via some particles of air, or I don't know what, but there could be some correlations that are pre-established between this ABC, right? There could be another mechanism, some other source here in the middle that you don't see, but that would distribute, you know, common variables to A, B, and C. And so if there could exist such a source, then you cannot claim that there is non-locality anymore, right? Because you see, if you put one source in the middle, that source can sample from the distribution PABC. And of course, then you reproduce it, right? No mystery. So somehow you need the assumption of independence, right? That the information that is used by this box to generate that outcome comes from this and from that, but that there cannot be a common source distributing data to everyone, right?
Okay, thank you. More questions?
Can you say something about what EPR says for quantum field theory?
So you mean whether there is non-locality in quantum field theory?
It can't be right because quantum field theory is Lorentzian. So what does it mean actually?
Aha. Okay, so here is an important point that is a point of terminology. Okay, that in quantum field theory and high energy physics, locality or non-locality is often referred to mean whether you have non-signaling or signaling. Okay, for us here, non-locality and non-signaling are two different things. Okay, so you see all these phenomena here that you can even generate in the lab, right? What you see is that the correlations that you get between the measurements results are extremely strong, but you can never use these correlations to signal faster than light. Okay, this is a key point, right? And in fact, the reason why you cannot use them to signal is because the measurement results, they are inherently random. Okay, so Alice can choose which measurement to make, but the result that will come out is fundamentally random, right? And so that's why she cannot use this effect to communicate instantaneously. So you see randomness, non-locality, and non-signaling, they are connected. And so you see, therefore, of course, all of these things you can also describe within quantum field theory, right? Here it's non-relativistic quantum mechanics, but you will also get it there. Okay?
Thank you. More questions? I guess then we can thank Nicolas Brunner again. And